also until more or less 3. Then we go for coffee break, some 15 minutes or half an hour. Then we come back until 4:30. We have the room. So yeah, and we can discuss also.
Okay, good afternoon, everyone. So let's start from where we finished last day. I was talking about how to construct radiative models, right? So yeah, already I discussed about these things. So what so far we learned, like we can categorize in uh, 2 type of radiative mechanism, like type 1, where you obtain, like as I showed yesterday, like you obtain from effective dimension 7, 9, 11 operators with delta L equals to 2 selection rule. So you can work it out and all these operators, and then you open up, you will get some models also, how to construct. I already talked about these things. And the type 2 radiative models, the other one where there is no new standard model particle inside the loop. And these class of models generally do not predict neutrino non-standard interaction, which I will cover a bit later. So these are the 2 class of models in the radiative mechanism. As you see, like all the particles inside the loops are basically BSM particles. And also I have discussed, I think I just want to give you one model example. Already we have discussed nu alpha L, nu beta L. Let's start with say L, and then you have LR, then you have this B5 plus, this beta plus. Let's talk about just one model when these 2 Higgs are getting waved. There is no right-handed neutrino, and this is the G model where you require no right-handed neutrino is introduced. Here you have a second Higgs doublet and a weak singlet, which I am writing down here. I think I showed you yesterday how you can come up with these models, like from the dimension 7 operator. So this is the one of the simplest model you can write down. Here I am just showing the model detail. Like you have this 2 doublet in addition to the standard model Higgs, you have a second doublet, and you can write down these interactions. And basically you get neutrino mass from there, this diagram. As you can see, also I will give you one, those who are not familiar with, you can do some rough estimation from this type of diagram. Say, how do I know without doing in detail calculation from the dimensional argument I am getting some right order of neutrino mass or not? Let's work out one. So suppose this is the F Yukawa, which I am writing down, and this is suppose a Y Yukawa. And so then the neutrino mass will be something like this is 1 loop. So there will be 1/16 pi square. From the loop factor, I showed you also this expression, generic expression, 1/16 pi square to the power n. In this case, this is 1 loop, so there will be 1/16 pi square. Then you have this F Yukawa, just without writing explicitly. And since there is a chirality flipping happening, there will be a ML. Okay, and there are so this is a Higgs wave, so there will be 2 V electroic square. Let me try to write it down. The heaviest scale will be m beta square plus m pi square. Let's look at the dimension only. And then there will be V electroic square. And there will be a logarithmic factor and so on. So this is the way I looked at it. So you have 1 loop, so that's why I wrote down 1/16 pi square. Then you have F Yukawa, you are starting from here, then here this V electroic insertion. Then there is another Yukawa, which I'm writing down Y. And then you have chirality suppression there, because in this type of diagram, if there is chirality flipping happening, the whole this neutrino mass contribution is proportional to that particular mass. And then the inside the loop, whichever the heaviest particle square, that will be the denominator. In this way, you can write down and roughly estimate, suppose I 1.1 EV, and this is suppose say 10 to the power -2, you can work out what you need for this type of scale needs to be to generate neutrino mass size.
What about the coupling, the three scalars coupling? So we have the dimension coupling.
Yeah, that's I'm writing down in terms of the electroweak. Yeah, of course, there will be a term. Okay, let me. Yeah, so this will be some sine theta or something. Yeah, there will be a sine theta term. That's correct. So between this eta plus and phi plus mixing, and which involves this cubic coupling over this the scale of the mass square. So in this type of cases now, I have shown just this is okay. Let me just point out one more thing, that this F Yukawa, if you look at it, this will be kind of anti-symmetric. So whatever you will populate just this type of term in the mass matrix. I'm not writing down. So this F Yukawa will be anti-symmetric, and Y Yukawa is completely free. Here I'm showing the structure. Y is completely free, but in 1980, the Wolfenstein version was like all these couplings are diagonal. If you take only these three diagonal terms, this is called Wolfenstein version of the G model. If you take that, you cannot generate the flavor structure. Flavor structure, I mean, you know the neutrino do admixture. If you multiply F times Y, that will not generate the neutrino mixing properly. So that version is completely ruled out. So you need to take into account the full general matrix for the second doublet, which is talking to lepton and neutrino. And as I said, like last day also I talked about it, that M nu Ij, how you can translate this Yukawa combination in terms of this neutrino oscillation parameter. Then you do the same task here to fit in a particular model, how you can generate the structure from the. So just I will flash out like some of the simple models. So here also like another radiative model, which is popularly known as G-Babu model. Here there is no right-handed neutrino, but you have two SU12 singlet, single charge and double charge scalar fields. And then you can come up with this two loop. And there, if you see the expression also here, what I'm writing, instead of 16 pi square, you have a 16 pi square whole square because it's two loop. And then this cubic couplings mu over m square, whichever the heaviest scale involved, that will go in the denominator. And then F AC coupling is this one, and H coupling is this one, and you have MC and MD, and then F dagger is like that's dagger, and this is the logarithmic factor which is appearing there in these two loop categories. So this is the two loop version of the G-Babu model, although like it looks complicated, but just the particle extension you are doing with standard model, just two scalar, two singlet scalar, and you do not require right-handed neutrino. Same thing you can continue like for three loop also, where you can go through the singlet Fermion and two singlet scalar, then you can construct such loop model. But this is my personal point of view. If you are introducing Fermion, more Fermion in addition to the standard model Fermion spectrum, I do not find it quite motivating to go to radiative models. Like, but of course you can do, and this type of models also generates to NSI. By the way, one point I should mention, yesterday I shown some generic expression. There are some papers where you can look at the literature, you will see that if you're going beyond 5 loop, because of this 1/16 pi square to the power 5, this suppression, if you go beyond 5 loop, I think neutrino mass will be too negligible. So basically people, that's why work out up to 3 loop, most of the models, if you discuss that. And yeah, please.
Is there either any like particular motivation for people to, is it just curiosity to look for three loops instead of keeping to two loops? Are there other features of this particular model that are
Yeah,
explain other things, but not
Yeah.
only the neutrino masses? Because
yeah.
you should start at two.
Yeah. No, that's a good point. But why I do this thing, I can tell you, justify the motivation. Whenever you have a extra suppression from 16 pi square cube, automatically these scalars are light scale and the Yukawas are also large compared to the other model. That's the only motivation, nothing else. Okay, so
And this is also not chirality suppressive, right?
sorry.
Is this chirality suppressive?
Yeah, this is kind
Oh,
of
that's also.
this is chirality suppressed because if you see that it's going through the yeah. Because at the end of the day, you need two Higgs insertion. I think yesterday I draw a diagram. I think there are kind of four graphs I draw. This belongs to this category. Nu alpha L, nu beta L. I think I draw this H. Yeah, this topology particularly. If you try to work it out, this is the same thing. Like here, basically you have H and you have H here. So, yeah, but I agree. Like this comes from the opening up the operator. You will see that not like they want at the first place three loop, but they are looking at the operator which can give the completion. You will automatically come out, or maybe if you open up from this type of graph and then try to see what type of particle you need, then you will end up with this thing. Only advantage, as I said, the Yukawa will be large and the scale will be low. So you will have strong prediction. Either it will be ruled out or tested. Like that's the only thing. Otherwise, yeah.
So I have this between yesterday, how can you say that these scale of the particles to be light? But how can you say that the Yukawa needs to be large? Like the Yukawa is free? Or
Yeah, Yukawa is free. As you see the any expression, like it's sorry. That's no, it's not one. Oh, no, now it's on. So you see that if you look at the neutrino mass, like there is F and Y, right? So it's a in the numerator, suppose there is a Yukawa coupling combination going over mass square. Okay. So if the new physics scale is lower, M scale is lower, then Yukawa can be higher, right? It's a compensating, you have C over lambda.
Yeah, it's just you are just bounded by the neutrino mass. K.
Yeah,
That's
so new,
very-
yeah, that's the starting point. Like, so also like another thing I want to mention, some of these models, like suppose say predicts normal, like which is normal, suppose in two loop G Babu model, like generally you expect the inverted ordering is not so favorable. And the lightest neutrino mass is zero in the initial model like which I proposed.
But can you see this from the diagram?
Yeah, from the diagram, you will see that the mass which is proportional to the, yeah, so the thing is that there is a singlet coupling going there. As I said, one anti-symmetric matrix is going there. You will lose there some degree of freedom. So you have three diagonal entry, 0, and you have another Yukawa. And you will see that if you compute, you have not enough freedom to fill the three angles and the masses. So yeah, different model predicts. So suppose say in grand unified theory also some of the particular type of modeling, some of the models people, but I'm not working on it. But, yeah. So three loop KNT model, I'm just showing you flashing out like one each example because to show that each of these has some colored version. So earlier I showed like you are going through the lepton. Now if you replace lepton with down quark, then you replace this non-colored scalar by this colored scalar, which are called leptoquark. And then instead of charge lepton mass, it gets proportional to the down quark mass. Okay. So same thing you can do, and in the neutrino mass calculation, there will be extra 3 factor from the color for the rough estimation, I mean. So if you want to naively estimate what will be, there will be extra color factor 3. So you can see in the diagram also 3, there is a mixing sin to phi, and then you will logarithmic factor, and then this y prime, and mass of down quark. And that's the function conjugate part. So that's how generally basically you do this radiative mass model building construction. Here also you require just 2 scalar field. One is C216 and 31 minus 1/3. These are also people give defined nomenclature for 311 minus 1/3. As I said, there are only 4 leptoquark possible. 3-1 minus 1/3 also people call it S1 type of leptoquark. And 3216 people call it R2 tilde.
What are the M1 in the long?
Sorry.
M1 and M2 in the long.
Yeah, these are the mass scale of this. So same thing also you can do for the G Babu model. What you did, like instead of charge lepton, you can go through the down quark, and you can do the same exercise. So basically, diagram is same and everything is same. Just you are replacing lepton by down quark. Then you know that what type of leptoquark you need diagrammatically, and then you can through the leptoquark mediated loop model, you can write it down. And also here you require 2 scalars, which is 3216 and 31 minus 1/3. So that's it. Also same thing you can do for the 3 loop, which one I just showed, KNT model people said. Just go through the down quark, then the same exercise you can do. So basically to warm up, you can do just 1 for the non-color scalar, and you can replace that, and with that you can do the complete the diagram, and you can estimate these things.
Any of these model can we have a dark matter?
Sorry.
We have a dark matter candidate, any of the model explained here.
This class of model has no dark matter, because this I'm writing down neutrino mass models in standard model gas theories without assuming any discrete symmetry or anything. But as I said, there is a class of model where you call it type 2 type of models, where there is no particle inside the loop is standard model. And then you get that. Then if you just impose G2 symmetry, it will be automatically stable. Okay. But if there is standard model particle inside the loop, there is at least a standard model particle inside the loop, then you cannot have that. That's the main idea of the scotogenic model. That you start with new alpha L, new beta L, and inside the loop, all the particles are BSM particles. So then if you input G2 symmetry, still these UCA couplings, you can write it down. But since all are like, it will make this dark matter stable, like the ones that.
Those are also well motivated, I guess. Those are also well motivated.
Yeah,
Yes.
yeah. Those are also well motivated, like in a sense that with imposing some G2 symmetry, maybe let's solve the diagram and explain it for you. So Sen was asking about this type of model. Let me explain it to you. So you start with new alpha L, new beta L, and you know that there should be L H H, right? To have the neutrino mass. Now, instead of standard model any fermion or standard model leptons or standard model quarks, as I said, if you go through the lepton, then you require non-color scalar. If you are going through the quarks, then you require color scalar, which is leptoquark. But now, if you imagine you want to go through some new fermion, you are introducing some new fermions. I do not want to go through any standard model particle. Then you can construct such diagram, and you, as I showed yesterday, how to compute what type of particle it can be. It can be scalar, what should be its charge under this, and so on. But if you look at this diagram, If you impose some G2 symmetry, all the particles are charged under this G2 symmetry. So then what will happen? The particle which is lightest among these two, that will serve as a dark matter candidate. Okay, so these are called as scotogenic model. So you can also do defined version of it and so on. So that's also differently motivated, that neutrino mass and dark matter you can get in a similar setup. But this type from the neutrino non-standard interaction point of view, these doesn't lead to neutrino non-standard interaction. So yeah, that's it basically to summarize all these things for the radiating mechanism. So far, anybody has any questions? No, but you get the overview, like how generally people do. If you are interested enough on model building, you can zoom in and look into detail, or you can discuss. But I give the overview how you can take two approach, either diagrammatically or like operator-based approach you can do. And you know, if you know that what type of particle you require, then you can work out this model very easily. Now the thing is that let's talk about the Dirac neutrino mass models very quickly. I don't want to confuse too much, but so for the Dirac case, let me write it down. So as I said yesterday, like if just introduce right-handed neutrino, and then you can write down such term like which generally if you take order of y like order of 10 to the minus 12 or so, then you will get the correct order of neutrino mass, like Dirac neutrino mass, you can write it down. Then the thing is that like as I said, like if you introduce right-handed neutrino singlet, suppose the right-handed neutrino singlet, and it's not charged under any new symmetry or anything, you can write down also Majorana mass term. So like there are different motivations. So how to protect this Majorana mass term from the theory? So people whenever do construct Dirac neutrino mass model, if this is a real issue, like this smallness of this Yukawa, if you think that's the issue, also people try to construct Dirac neutrino mass model, how they can explain the smallness of this Yukawa. To do that, what are the requirements you need? You need to ensure that Majorana mass term is protected by some symmetry. Otherwise, always you can write down, you need to justify what is the reason behind you are taking some terms to be zero. Okay, so people impose discrete symmetry. I think yesterday I also said that since discrete symmetry like does respect this global symmetry, this is not respected by gravitational correction, so it will lead to some lepton number violating term at the Planck scale, which is suppressed, but it can be there, so it will be in pseudo-Dirac type of nature basically. But if you gauge it, so this problem is not there. So let's show one example so that you understand what I'm trying to say. So in standard model, you can write down this. To explain the smallness, if you are trying to construct Dirac neutrino mass model, instead of writing this, let's try to write down some new operator. I'll just give you one example, like how to do this. So I'll assign charge such a way that I cannot write down this L bar H tilde nu r, but this is invariant, Li H bar nu r sigma. So if I can do that, so then if you protect that and if try to generate this operator, this is a you see that dimension 5 operator. You can write it down. Let's try to construct one example. Say with standard model, you impose some U1 B minus A. Okay. Let's write down all the charges. Oh, the charges are gone. Sure. Here I'll explain why I'm writing like this. Fields. Okay. So as you can see, I want to write down such terms like under this, like these are the charges which I said yesterday. This is SU3 color, SU2L, U1Y, and this is U1B minus L. And this U1B minus L, you are gauging it. As you can see that this term you cannot write it down because L bar is 1, H tilde, this is 0, and nu r. So let me also write down one more things that whenever you are trying to construct any like model, generally you need to take care of the triangular anomaly comes from different gauge group. So to do that, there will be certain condition you need to satisfy, and you will see that in U1B minus L scenario, there are only two anomaly free combination. Nu r charge can be -1, -1, -1, or nu r charge can be 5, -4, -4. Okay. So these are the two anomaly free combination you can write down in U1B minus L extension. And suppose you know you want to explain the smallness of this U cover, you can do radiatively. So if you do not want to generate in tree level, I think you need to prohibit this term rather than if you take this type of. That's why I just for one example I'm showing you this charge combination. So as I said, this is 1, 0, and 5 or 1, 0, 4. That is not allowed. But if you see 1, -4, and 3, the sigma is compensating this total. Did you understand this thing? So it's 1, like I'm taking a look at the U1B minus L charges. 1, 0, and this is -4, and this is 3. So this is properly cancelling out. So that's how I want to generate this operator. And that's why all the particles you require, these are the charges, these are the standard charges, and these are the U1B minus L charges. Now, let's take a look what we have done yesterday. So you will take the similar approach, like by a similar approach, I mean, suppose for example, you have 4 field L, H, nu, sigma. how many diagrams you can draw for the one loop. Suppose you want to generate one loop diagrams. Let me draw those diagrams for you. Yeah, this is fun, but I'll show you how to.
So the first, the new arm cannot couple, so is that the case because of the charge?
Yeah,
They don't couple.
yeah, they don't come. Yeah. You are taking some particular representation such a way that doesn't come. So another thing I should mention that to explain neutrino oscillation data, if you are adding right-handed neutrino, you know that at least you need 2 generation of right-handed neutrinos. Otherwise, you cannot satisfy the neutrino oscillation data. Just with one right-handed neutrino extension, no other particle extension in the scalar sector, you cannot generate neutrino oscillation data. At least you require 2 neutrinos. Again, I'm saying while I'm not extending the scalar sector. So now let me see. So I want to construct such operator for Dirac neutrino mass models where I'm writing like new L bar, new R type of term. And with the 4 field, I can draw such 6 type of graph. Now you will say that it will immediately end up with very few graphs. Can anybody tell like one diagram? You can clearly see that it's ruled out by some like whatever I tell yesterday. Anybody has any idea? Which diagram is not possible? If I'm writing down a renormalizable gas theory, out of these 4, like with the 4 field, I want one loop graph, suppose say. Do whatever you want. These are the possible way you can do. Out of which one graph will be automatically ruled out. Okay, so this diagram is ruled out. The reason is that still you can follow like why it is. You see, I need at least 2 fields should be L and nu R, right? If I'm writing, so either this or either this. So if I'm writing dimension 3 already here, if I need a 4 field vertex, it's already dimension 5. This is not allowed. So automatically this will be like this diagram is like will not need to take into account. Okay. So now another 2 diagram will be automatically cancelled out. Suppose if I am trying to generate the radiative level, so this diagram is not valid anymore. Now you can see that also this type of 2 diagram, like for to get neutrino mass, at least I need L nu R somewhere, right? So if I can generate this type of term, whatever the from the charge assignment, you can calculate the scalars charges, what it can be from there, you'll see that that will generate the tree level mass. Okay. So if it is generating already tree level mass, it's like for both the cases, it will generate tree level masses. From just playing with the charges, you can see that it doesn't contribute to anything new. So the 3 of the diagrams are already invalid.
So can you repeat the 3 level mass?
Sorry.
Can you repeat?
Yeah. So suppose this L and nu R. Look at the charges. Okay, 1, 2, minus half, minus 1, and 1, 1, 0, suppose to minus 4. Scalar you require here, that has to have some U1 V minus the charge. Okay, and that will generate the 3 level mass. I do not need to go through one loop. This will be subdominant effect. Okay, so that's why I'm just telling that.
I thought Here, the scalar need to be doubled in this case, or,
Which one?
again, this diagram, you said
Yeah.
it level, but it had to be doubled, right?
Yeah,
But if you don't have this particle, okay.
no, but this is Dirac mass term, right? It's not like I'm talking about Dirac neutrino mass at the tree level.
So you have to add a doublet scalar.
Yeah, of course. You need to add a doublet scalar and its nature will be 1 to minus of 3. If you compute, I think you can see the charges will be 1 to half. Yes. So, okay, so this way you can discriminate and then you will end up with such models. And there also you are opening it up. I do not want to complicate, just I am saying that although there are many possibilities, you will see that if you work out systematically, it's not like there are like many ways you can do that. So then you will end up with these 3 diagrams. Even if I do not want to draw such diagrams, I just will show you in the slides. Yeah, this I already have shown.
What do you focus on? The loop itself, the tree level for the.
To explain the smallness, of the Yukawa, suppose say, because like, of course, this is differently motivated, like if you introduce just with Higgs, like you can write down with the minus 12, like you can write down the Dirac neutrino mass. But suppose say it's bothering you that I want to explain the smallness also.
But you can use, it's like how to generate the higher dimensional operator at tree level, no, it's possible, right?
Yeah, that's also possible. Yeah, that's also possible. That also I am going to tell you. Like there are similar sort of analog of the type 1, type 2, and type 3, which you can do that. Yeah, that is one way. Since I am discussing about the radiative models, I just want to finish the graphical approach, like how you can do for the Dirac neutrino mass models also. Yeah, but you are right, like you can do the same thing for the seesaw analog to this kind of scenarios. So if you look at this third topology, like the bottoms all are like you don't need to take care. So the third one also, there will be many diagrams. So, and how you do these diagrams, like basically sigma and H placement is just different. If you see L nu 1, you are starting with a scalar loop, then you will have one diagram. At the end of the day, you need L nu r sigma H, like these 4 fields. Then you can do the same thing with the fermions. And also you can do the admixture, and then the sigma and H position, if you can, or like interchange, that will lead to some other graphs also. But out of which also you will see these 2 graphs are will generate the tree level mass. Just I'll ask you to think about it, and you can do by yourself, like because the scalar you need here, this will also generate the tree level masses and so on. So this way you can eliminate one after another diagram, and you will see there will be some finite possibility you can work out. Okay, so those who are interested, they can do that. At the end of the day, you will end up with only these versions of these models. Like this is exactly same what I told you in G model. So you have L and L is going inside. Instead of that, you have L and nu r. You have right-handed neutrino. But instead of L H, you have now L nu r H sigma. Okay. But the other tasks are exactly same. So due to this U1 B minus L symmetry, basically you are generating Dirac neutrino mass. This is also, you can say, G version of the Dirac neutrino mass models. So I'm just saying that there are all analogs of the Majorana neutrino mass models also, like depending on the symmetry you import, exactly same model. And you can repeat the same things, like I showed you also this type of graphs where 2 Higgs are appearing like this on the same side, or depending on the positions, you can draw those graphs. And you can basically write down how many OA you can write it down. Like, and there will be some finite possibility you can write it down. For each topology, there would be like, I think 3, 3, 6, 9 class of models, suppose a 9, 10 class of model you can write. Okay, so the main thing is that what I want to emphasize that you do not need to do, but if you are curious about how to generate neutrino masses and mixing in different scenario, whether it's a Dirac or Majorana. So there are some prescription you can do like in a systematic way. So what can be the minimal approach I can take, what particle spectrum I need, and then write down the Lagrangian, and you can automatically see whether you can satisfy the requirements.
All of these models just explain the smallness of the curve, but they do not say anything about the hierarchy of the PMS strategy.
No, no. I'm just here just purely showing the mass model construction. There is no prediction from the PMNS or the yeah. So the same thing also, just I'm saying that replace all the charge leptons. One thing at least take home message is that if you replace with quarks, this will be color scalar and do the same task, you can just continue. So then you will end up with these Dirac mass models, and then you can also list down all these. And then for the two loop graph, it's very weird, but how many OA you can write it down, then there will be too many OAs. And you do not need to worry about that. Like half of those diagrams will not give rise to anything. And you can basically give these kind of 6 topological, like 6 basically graphical structure, where you can also, the third diagram is called sunset diagrams. So you can do the same thing, and I'm not talking about all these details. Just if you replace sigma and H, yeah. Yeah.
There is a systematic way to know how many loops will appear, like you show all of the possible, but I meant that people had to go to all of them separately to see that they're.
Yeah, up to 2 loops for the Dirac mass model to have one.
Yeah, but is there a systematic way to know before we calculate how many loops you?
No. You need to sit down and do all the diagrams, and also what is your starting point? What is the operator you are writing down? And what is the minimal particle you require? Also for this, if you want to generate in the loop level, at least a sigma particle should be there. I should not write down the, if I can write down that term, so what is the point of taking this type of Dirac?
From the point of view of experimental searches, the Dirac mass models where the particles decided to power, these are more constrained, right?
Yeah, these color particles are more constant. So, yeah, this is just purely like how to do in a systematic way this model construction. There is no motivation why you will do that, or like this is the overall summary, how you can work out by yourself, like what type of model you can come up. Okay, so yeah, that's it. So that's the kind of summary I gave, like from the neutrino mass model building point of view. You can do tree level. First, I showed the tree level case scenarios. Then I discussed the through the quantum loop correction, how you can construct neutrino mass model. Mostly in these cases, you need some scalar extension rather than harmonic extension. Whereas, like you see in the tree level, like mostly people do right-handed neutrino extension. Of course, you have type 2 seesaw where scalar extension also can lead to some tree level neutrino masses. So that's the overall summary. Like if you try to do neutrino mass model building, that's it. But all these mass models, suppose say you see that there are too many particles, not too many, like whatever the minimally required particle you need. But how do I can test? There are so many possibilities. As I yesterday mentioned, there is another way of looking at it. There should be some certain distinction between these models or these mechanisms. So and it's comes to the then it becomes very important how neutrino interacting here with the matters. In different models, you will develop different sort of neutrino non-standard interaction or neutrino electromagnetic properties. So without looking each individual particles, then you pay attention to the neutrino interaction with the matter fields, say electrons or up or down. That I will basically talk about, as I already mentioned, the third category, like how neutrino talks to without knowing in detail, like what is inside the block, whether I can write down some photon interaction, like in the Wolfenstein version, like then if you have some new interaction, I already showed this also, this type of diagrams that in standard model, before going to neutrino non-standard interaction, you have neutrino standard interactions. As I showed you here, these are the two standard interaction. The left diagram is the charge current interaction, and the right diagram is the neutral current interaction. The right diagram is flavor universal. As you see, there are nu E, nu mu, nu tau. But the left diagram has something special on nu E, which develops the matter potential I discussed during the MSW effect discussion. So on top of this, whenever you are generating neutrino masses and mixing, always you generate some new interactions. On top of these two diagrams, there are either via scalar exchange or due to right-handed neutrinos presence, you can draw a separate diagram which is contributing to neutrino non-standard interaction. So you can write down these operators like this, as I showed here, like these are the neutral current neutrino non-standard interaction. What is neutrino non-standard interaction? I showed you for the muon decay, how you can write down the four Fermi operators. Similarly, you can write down neutrino, neutrino, fermion, fermion. It can be up, down, or electron. Here, this P is the projection operator. P can be PL or P right. But for the neutrinos, like in standard model, if you are working it out, it's the only left-handed projection operator. So then you write down this epsilon, this alpha and beta defines the neutrinos flavor index. So with compared to G Fermi, how enhanced you can get, and that is called neutrino non-standard interaction. Basically, this type of interaction. If you have a new interaction, you can integrate it out. You can do the Fourier transformation and write down in terms of this neutral current NSI and charge current ASI. So and here also I showed like NSI which affecting in the production, NSI affecting in the detection, and NSI affecting in the propagation. So this type of operator generally leads to this sensitivity to different places like production or detection or propagation. By the way, the most important effect of NSI is in neutrino propagation in matter, which we already discussed or which was proposed by Wolfenstein. There are variety of phenomenological studies, like if you have NSI 1% or 10%, what sort of effect you can expect in different places and so on, which I'll discuss in a while. But there are very few activities are going on, like how do you realize, suppose this type of NSI you realize there are so much effort going on, this NSI you realize in suppose in 10 years, I saw some NSI effect. But you need to come up with some scenario or theory, like where you are generating neutrino mass and mixing, and that can lead to NSI. Because it's also suffer from whenever you try to generate, like it's very well connected. In standard model, charge lepton flavor violation is not there. So you basically do this lepton, charge lepton flavor violation through the neutrino oscillation, right? When neutrino has mixing, then you develop this thing. So whenever this neutrino non-standard interaction you have, because in standard model neutrinos are left-handed, you have charge lepton partner also. Always you induce some charge lepton flavor violation. That strongly constrain this. That's the major challenge for getting sizable NSI, this charge lepton flavor violation. And then I will just show you like in different places where you can look for this type of NSI. So suppose say the model I discussed, say G model, where you have some charge scalar instead of W and G. In addition to that, you have some interaction with the charge scalar, and that leads to some new interaction. And you can then write down after Fourier transformation, you can see there are four contributions which is appearing with the exchange of two type of scalar you introduced, that will lead to some NSI strength which will go like Yukawa coupling combination and the charge Higgs mass square. And this same Yukawa and charge Higgs mass combination also appearing in the neutrino mass matrix. So while you are trying to compute the neutrino, like from the neutrino oscillation data, if you are trying to feed that, if you have a definitive scale, then you will predict a like the NSI strength for that particular class of models. And whenever like you are considering these, I think there are many things you need to take into account. I am not going in detail. You need to be very careful about electrointensity parameter, electron flavor violation, as I said. But there are some tricks also you can do how you can satisfy the neutrino oscillation data without doing charge electron flavor violation. And then we find like something like in this type of models, like in these radiating models in the G model, these are different size of the NSI compared to G Fermi, what you can get in this type of model. So whenever you generate the neutrino oscillation data correctly, we are getting some sizable NSI there. As I said, it goes like you coupling combination of over this charge Higgs mass square times some mixing, which also appearing in the neutrino mass matrix. So I'm not going each cases like, but just if you have some questions, how you can get that and so on, I can tell you in detail. But then we categorize all these models, as I said, like in two categories, type 1 and type 2, where we find that type 2 type of models, like where there is no standard model particle inside the loop, almost like it's a zero NSI. You do not expect any neutrino non-standard interaction because you are not generating those type of electron number violating operator. But if you are in type 1 class of model, you can categorize in, we find that we did some systematic study and we find like 6 classes. And in the 6th class, like defined model can have maximum sizable because there are 6 scenarios, as I showed, like epsilon, alpha, beta, alpha and beta determines two different neutrino flavors. You can write down 6 cases. And for each class of model, where G model, and then this is called minimal radiative inverse, so that's also one loop model. And then the other leptoquarks model also worked out. For different models, you will have a different kind of size of prediction. And whenever you will feed the neutrino oscillation data, you can see that in one place, if you are appearing one particular prediction, in other NSI, you will have a different kind of prediction. From that, you can get some idea of the texture of the matrix. So, yeah.
This is 100% means epsilon 1, right?
Yeah. That's the G Fermi. We compare to G Fermi, how much you can achieve in this class. And
This is not 20.
yeah, these are suppose electronic NSI. And also like I have not discussed here, but even if for the right-handed neutrino extension, you can draw such diagrams. You have W and G interaction. So anyway, now I can have say N. Yeah. So if you have some right-handed neutrino in addition to the standard, so then you, in addition to this W and G interaction through the mixing, you will get some effective this type of nu E interaction. And also you can do change the same things for nu mu or nu tau. You will get the some and it will deviate this U matrix which I have written. You will violate from the, like you will shift from the unitarity. So, and that will determine, so the, suppose say the epsilon EE will be proportional to the UE4 square. If you have a fourth sterile neutrino or right-handed neutrino through the mixing, then it will be proportional to that UE4 square. Epsilon mu mu, or like U mu 4. So maybe we can stop here, and then after the break, I'll talk about some other places this interaction how to go.
So in these cases, you send the equality one, sorry, the equality to the new particulars with the electrons, you set it to be one.
So yeah,
Then you go up, the new coupling.
no, you need to vary it, like, because you coupling will be determined by the neutrino oscillation rate.
You marginalize it.
Yeah, you need to marginalize. Because also you need to generate all the mixing angles and so on. You do not have much room actually. Because already, suppose say for one example I'm just giving, I show you the F and Y you cover. If already 3 entries are 0. So you have 3 degrees of freedom in the Y you cover. And there is another Y you cover. There are 9 entries, 9, 3, 12. But I think then from the neutrino oscillation data, you have 9 things to fit, right? So then you can fit, whenever you try to fit out to get the texture, you will see that it taking some particular pattern or defined in SI, you will have defined prediction.
Did you have considered ordering normal and inverted?
Yeah, we also did that. I think for inverted ordering, we are getting an SI not sided. For normal ordering, we are getting some sided SI.
These are normal.
No, this is for some cases, suppose a minimal radiative inverse is a model, some scenarios inverted ordering also giving the higher prediction. So it's more detail of the models, okay? So it's the optimized scenario, no matter what in a particular model, maximum you can achieve of this. For that, you need to do work for all electric precision constants, the favor observable provider, and also like I said, also going by what generating neutrino oscillation with like it will give some pattern. It's very complicated and chaotic, but you can do that. So, but the one good thing is that suppose that these type of models are realized, or like some NSI has been realized in upcoming years, because you are putting too much effort on these neutrinos experiments, scattering experiment or oscillation experiment, you realize some NSI. So then you will look back which class of models can predict that. Then you will see that they will have different definitive prediction, either in charge electron favor violation or in collider or in electric precision constant. So all these models have defined kind of signature or defined prediction. And also then you look for, suppose a defined flavor in SI, you will have also different prediction for different models. So you need to do some complementary test on this type of thing. Yeah. Maybe we can take a look then wait.
Yeah.
To be back.
So now we will take a break and we will be back in 20 to 30 minutes.
Yeah, because people usually say they can depend on each other, but from this, but they are very different.
Yeah,
Yeah. Because because I think you can distinguish both of these materials. I'm not sure if I know that, but I think these two should be distinguishable, whether it's really strong. Yeah, that's actually non-intermediate.
Yeah, I think you wrote a paper on
Yeah,
that.
but I'm not sure, yeah, really,
Yeah.
that's actually, but, yeah.
No, I understand your point. Yeah. Whether that is related with the CTP or not, so. So far I discussed about in defined neutrino mass model. So the main message which I tried to portray that from the complementarity and defined signatures, neutrino mass model can have defined prediction for neutrino non-standard interactions. Okay, so now let's take a look. Like I'll try to give an overview that where and what you can look for and define frontiers. So whether it's collider or neutrino experiment or some astrophysical neutrino, astrophysical sources like some neutrino telescope, where we can look for defined signature for the neutrino mass models, or how we can say something about it. I'll just give some overview. First, let's start about in Europe, like this Large Hadron Collider. So in these LHC, what we can say about defined models? It's not a complete list, but I just give you an overview so that you understand what we can expect. Not necessarily that, again, I'm telling you that as I showed you, the neutrino mass messenger doesn't need to be at the TeV scale to be probed at collider. But you can have your favorite scenario where you can make in the lower scale, and as I showed you in a diagram like LHC and different dimensional operator, if you have, so then you will have some lower scale prediction. So suppose say if it is predictable at collider, say TeV or sub TeV scale, some new physics, say right-handed neutrino, what you can expect? You can expect, suppose say from the T-level seesaw model, I'm showing here, if you have weak singlet fermion, say right-handed neutrino, you can expect some lepton number violating signature. Let me draw it here. So you can see that in the PP collision, you can produce same sign dilepton signature, which you do not expect if you do not have right-handed neutrino. You will always have lepton number violating signature because you are not starting with there is no lepton number violation here, but if you are ending up with in the PP collision, say L plus say one fat jet, or if you have say two jets, these you do not expect in standard model. But on the other hand, if you have say this is called standard type 1 seesaw, as you see in the diagram also, if you have right-handed neutrino, you can expect such signal in the collider. And if this right-handed neutrino in the sub TeV scale, it can probe this type of signal, because anyway you need to go through this lepton number violating signal. So the same thing also can be done for type 2 seesaw, as I showed you, like defined way of contracting that leads to some defined particle representation. So suppose if you have type 2 seesaw, what will be like in QQ fusion through the J gamma exchange, S channel, these are called Raelian, also Raelian process. You can go to say double charged, double minus. Okay, so what you will look for? You will look for 3P to say L plus, L minus. So this is the signal in collider. You are doing proton-proton collision, and your final state will be 4 lepton. And in collider, you can identify the charges. Okay. Then what you will do? You will reconstruct. You will pick up same sign leptons, and then you will reconstruct the invariant mass. So I will reconstruct invariant mass of L plus, and I will reconstruct invariant mass of L minus. If that leads to some resonance, suppose say in G boson signature, how you find? Like if you L plus, L minus, you reconstruct, you will get a sharp peak, right? Similarly, if you get a sharp peak like that, then you can conclude that there is some kind of double charge particles or something which is leading to this lepton number violating signature, like this L plus same sign dielectron signature, which you do not expect. No standard model particle can lead to such same sign dielectron resonances. So that is also expectation, which I'm showing it here in the second diagram. Similarly, like in addition to the this type 1 seesaw, if you have new right-handed current on top of this diagram, this is W, you will have another diagram with WR also. Okay, so then your production rate will be different. You will have a expectation of heavy gauge bosons and so on. You can look for such signals in left-right theory. And if it is collider accessible, you can look for such signal. There also you will expect some lepton number violating signature and so on. Just I'm giving an overview. So in collider, what you can look for in this type of models.
Will this be a good motivation to build a E minus collider or E plus collider?
Yeah.
To explore this kind of model.
Okay, so okay, let me tell you another thing. So for the lepton collider, radiative models are very sensitive. I'll explain you why. Let me share my. So suppose say, like all these diagrams, you see these diagrams already it's is there, like this type of coupling, these are weak couplings, G gamma couplings too, you cannot protect these things. So it is there, and even if this G gamma interaction with double charge particle also will be there. So it's just you will have such signal. So in PP collision, always you will produce that. Even if this diagram also through the W, L and A, if you are going through the type 1 seesaw, somehow the scale is suppressed in your scenario, so then you will always go through this. But imagine you have leptophilic models, like or suppose say G type of model, where you do not require any quark involvement. Okay, so if suppose say you can have a, like I already showed the diagrams. You have some eta plus and phi plus, which talks to neutrino and charged lepton. Let me show that. Yeah. L. So you see, this charge scalar supposed to talking to only lepton and neutrino. Okay. So in those kind of cases, the collider sensitivity will be quite low. But on the other hand, if you go to some lepton collider, you can expect some interesting signal, because in E plus E minus collider, like you can say there will be S channel and T channel exchanges. Sorry. Mu or tau, like, or anything like. And this type of couplings are coming from this Yukawa. Whenever you try to generate the neutrino oscillation data, you need all these non-zero entries, right? These are supposed to E entry, this is U mu entry, P tau entry, mu E, mu tau entry, tau E, tau mu, tau entry. So since it is a doublet, right? So doublet can talk to some neutral scalar is there. So through this coupling, which generates to neutrino oscillation data also, in E plus E minus collider, suppose you can probe such like this type of interactions very easily. And also you can have S channel, suppose say in E plus E minus collider, you have S channel G gamma exchange. You can produce that, say eta plus, eta minus, and then you look for L plus nu, L minus nu. These are similar to the searches which is in supersymmetry also people look for. These are called selectrons, muon or tau searches. So you will have L plus L minus plus missing ET type of signal. So in this type of radiative models where you do not require right-handed neutrino, but you are going through some leptophilic scalar which you require this type of coupling that can be probed well in the lepton colliders and so on.
You cannot actually know whether there's a lepton number relation.
Sorry,
You cannot tell whether there's a lepton number relation.
that's a very good question. So it's hard to tell in these type of cases that whether there is lepton number violation or not. Because it involves with missing ET, and if it involves with missing ET, then we are kind of blind. So in the collider, I cannot say for the G model, suppose whether it's leading to lepton number violation, like lepton number violation or not.
Yeah, because I'm thinking of the other model that you showed.
Yeah.
That delta plus plus to
Yeah.
to positron or
Yeah.
delta minus to electrons. If you use the lepton collider with the same electron, if you
Yeah.
can produce enough energy, it'll be a
Yeah.
very strong signal. No?
Oh, yes, of course, there it will be,
Very
yeah,
clean.
yeah, very clean, like, yeah, you are right, E minus E plus, and then whether it's a mu, E minus E plus or muon collider also, you can do that. To G gamma, you produce delta double plus, delta double minus. And if you, even if you give some tag like E mu, like different flavor, it's very clean. Because you do not have any flavor violation also. On top of that, you are collecting mu and with same sign, and then it's pretty clean signal. Anyway, these are the searches you can look for different messenger. Like, yeah, please.
So in the diagram that you wrote there,
Yeah.
with the doubler,
Yeah.
the final triggered leptons would also be right-handed.
Yeah.
So can you actually say if the triggered lepton is right-handed or left-handed in this type of experiments?
Yeah, I cannot do that, but if you do the through the WR, the transverse mass distribution will be different. Because from the W, if you do that, there is something called not invariant mass, like the transverse mass distribution. Generally, you see a distribution around 80 GeV. So if you have some heavier particle, so then its distribution will be different. From the kinematics, you can say something about it, whether
Yeah,
it's
but for example, I think the paper by was where it says that if you know if the electrons are right-handed or left-handed, then you can tell the neutrino as maybe is going through some new physics or
yeah,
just the Majorana.
yeah.
But can you actually say it's right-handed or left-handed? I understand that the transverse mass will tell you if that the behavior is handed.
Yeah.
But do you know if you can actually measure if the electron is left-handed or right-handed?
From the collider point of view, I think it's hard. It's very hard to say whether it's left-handed or right-handed. But in what Shane supposed to ask you, whenever you have control, so E plus E minus collider has this kind of facility. Like you can have control over the polarization. So yeah, ILC suppose, yeah, you know that what you are sending. So then, yeah, so in those cases, it is very sensitive, but in LHC, it's, yeah. So, yeah, but that's a good question. So, yeah, you are talking about basically this Keung-Segenovich process. And
Is that what I think? The last time I heard about it, some people say, oh, the only way to measure that is just throw your electrons to be on the tubes and wait until it interact.
yeah. Okay, so more or less in collider, that if you have different mediators, you can look for different signals. What I just said in a simple street type of seesaw scenario or radiative model, you can look for such signals, and collider, you can say something. But there is also another thing also, like maybe all these signals are not prompt. So your Yukawa is small, and that slips to non-prompt signature. So then you will not expect in collider any signals. rather you will look for a displaced vertex signals. Okay, all this seesaw scenario, if you see this n decays, suppose say these are too long-lived in nature. Okay, if these are too long-lived, then you should not expect any prompt signal in collider. So there are many activities are now going on for the long-lived neutral particle searches or single charged or double charged particle. So if it is neutral particle, the search strategy is different. From this displaced vertex, you can look for such signal. And if it is charged particle, these are called ionization energy loss. Whenever your charged particles you are producing, suppose this type of charged particle you produced at the collider, and then its lifetime is long enough, it keeps a track on the detector. So these are sometimes called disappearing track also. In supersymmetry, people do consider like if it leads some track and then produce some pion, it leads to disappearing track signature. And if it is long-lived enough, suppose say its a lifetime is almost like age of the universe. So then people do a quantitative measurement which is called DEDX. DEDX is the energy deposition. These are called ionization energy loss gradient. They do compute and see whether there is such long-lived particle. Okay, so the point is that you see then you do not need to rely on this Yukawa, whether it's small or not. As long as if you are producing this type of particle and this coupling is there, this coupling is there, you know that as long as you produced it, it will lead some track, ionization track or large ionization in the loss gradient. So looking at that, you can look for also such scenario. Yeah, please.
How much must the lifetime be for us to use the gas to this? Like how long should be?
Yeah, so okay, that's a very good question. So let me clarify this scenario, okay? There are two scenario Atlas and CMS are looking for. So in this type of Dralian, if you produce some long-lived particle in the collider, this beta or the velocity of this particle generally less than 0.8 or 0.7. Okay, that leads to different type of DDX signal if you look at the kinematic spectrum. And there is another possibility if you have some resonant particle, I don't know how it is, through the Higgs you producing such type of particles. For example, suppose say, if you are say this is some heavy Higgs which is decaying to this and that, so then what will happen? It will be too the boost will be super high. So in that case, beta will be almost like 1 or like 0.9 to 1. In those cases, like in standard model, you cannot get such thing. So those are called large ionization track. And for this type of cases, so then you see that there should be some parent particle which is decaying to this. Now you are asking about what is the traveling distance and so on. So different experiment has took different in the detectors are placed in different length. So I cannot from my head currently can tell you the distance, but you
It's about 1. It's about 1 meter.
Yeah, the first calculation of mistake is 4 meters from interaction points. The last one is about 100 meters. This would be the tracking. And if you're doing HSCP searches, you can also get signals from tunneling.
yeah.
These appealing tracks should be somewhat smaller.
If the weight is less than, let's say, 10^14, then it can scale it.
Yeah, so there are some cases like where it completely escapes the detector. You do not need to rely on how much distance, so it will leave some ionization track. Suppose say there is one axis which exists. You can look at this Jian Jirichi et al. Talk about it. Where they are saying that there are some DDX access in the very large ionization, which completely escaping the detector with beta greater than 1, they are finding lots of ionization energy deposition, those things. And the expectation was 0.4 or some events, but they are getting 7 events or so. And it is there for last 2 years to 3 years. So yeah, so whether these are true anomaly or it will go away, but irrespective of that, I'm just saying that not only it can reach to prompt signal. Some cases, suppose you are taking Yukawa small, like when you are trying to generate the neutrino mass or the structure, whenever you are trying to generate whatever the Yukawa require, if it is too small, even if as long as you are producing, it leads to some sort of signal, like from the disappearing crack or displaced vertex signature, you can look for in collider. Say, so you see, this is a direct search of neutrino mass messenger. And here I am giving some summary, like the same thing which I just mentioned. These are the current bound on type 1 seesaw from looking at inside dielectron plus jet. And the inverse seesaw, by the way, inverse seesaw, I mentioned to you that when this mu value, the lepton number violating term is too small. So you do not expect lepton number violation there in the collider signals. You expect lepton number conserving signal because that is pseudo Dirac in nature. Okay, I was showing the mu scale. If you are going very high, then you expect like the very high lepton number violating signals. But if your mu scale is too low, so then you will expect this type of trilepton plus missingnity, but that's nothing to do with lepton number violation because you cannot see such effects. And for the type 2 seesaw and type 3 seesaw, one interesting thing is that here you do not need to rely on the mixing. Your production, because it's triplet, SU12 triplet, you can always produce it. So only parameter is the mass. That's it, SU12 triplet mass. For the type 1 seesaw, suppose it relies on the mixing and mass. Because to produce it, you need to go through the mixing, as you see here. But for the triplet, you do not need to. Immediately you will produce because this is SU12 triplet, so you can produce it and then you look for signals. So that is more or less. Now, let me tell you another thing. So you look for some new particle which involving suppose a neutrino mass. You are looking for like what you can do if it is accessible, then you can look for such things. Now, even if NSI, you can look for in collider. How you can look for? So in dark matter search there are. So how you look for dark matter? So generally in WIMP scenario, WIMP miracle scenario. So you generally what you do, dark matter, there is a blob. And then basically you go to standard model. And what is the standard search of collider for the dark matter? That is basically you look for, you just swap the diagram. Basically standard model. In collider, you are colliding and then you are producing dark matter. And you look for monojet signature. So these standard model particles can be quark. So then in LHC, basically you look for in PP collision. So basically the signal is in PP collision, you look for missing ET because the dark matter leads to missing ET plus monojet. This gluon from the initial state, you radiate jet, and that's how you look for this interaction strength. And if you see this dark matter relic abundance plot as a function of mass, you will see there is some collider bound. This comes from this type of signature. It can be mono J or mono W or mono G, all you are radiating from here. Okay. So the same strategy you can look for, because I already discussed about this. You can write down the operator neutrino, fermion. Just replace dark matter by neutrino. Instead of dark matter, if you are writing down neutrino. So that leads to also monojet plus missingnity. Okay. So in collider, you can look for then this neutrino non-standard interaction like this way also. So here you are not relying on any particular particle involved in the model. Rather than you are looking for, you can effectively constrain this epsilon parameter from the collider missionity plus monojet signal. The same strategy, what you do for dark matter surges. Okay. So of course, like it's not like, as I said, that you reconstruct L plus L minus and it will give some sharp peak like golden type of resonance. No. It will be like huge background because missionity involved. But whenever you do the kinematics, you will see some, in the tail, you will see some signals distribution. And that's how you extract the data and put, suppose in dark matter bound. Similar way, you can directly probe for this neutrino non-standard interaction operator in the collider. Okay, and that's the plot which I did with Pedro, Babu, and Dorival. This suppose just take some, for simplicity, some G prime mediator. So it will give the effective treatment whenever you will go to higher mass, it will be just flat. If you go here more like, it will be like the NSI strength will be, you can give some bound, you can do the EFT treatment. So we are showing that if you are going lower and lower mass, so then this NSI NSI can be bounded from the current collider data, and which you can see for defined NSI, the neutrino experiments bounds are even if less stringent than the collider in some cases. Okay, so I'm just saying that this is complementary. If you are going to higher mass range, collider is getting very sensitive for this NSI strength, but whenever you are going to lower mass range, and that is quite expected. And this will give some nice complementarity also, because there are several degeneracy also is there in neutrino oscillation experiment. However, in collider experiments, that type of degeneracy can be removed because it's depend on the mediator mass and so on. So this is the epsilon E bound. This is just a number. So there are 6 type of NSI: epsilon E tau bound, epsilon mu mu in tau, epsilon mu tau. But if you are in collider, it's just complementary. Collider, you are blind to favor because this is missionity just. So you will have such bounds. So yeah,
Which bound? Sorry, what experiment did it for?
the black one.
Sorry, I mean the dash line. These are from.
Okay. That's like whenever, suppose say, whenever I'm writing say a quark neutrino, always I can remove the neutrinos and swap the diagram, and I can have dijet also, right? So you understand what I'm trying to say? So for the NSI, what I require, suppose it is A for quarks, quark, neutrino. Quark, neutrino. You have diagram like, you are starting with quark. I have suppose some G prime and it's going to neutrino. That's how you are trying to look for. But if you swap the diagram, I can have same model, same coupling, same everything can lead to also G prime goes to just flip the diagram. Yeah. So you will have dijet. So that's also tight, can put tight constant. So you need to be careful. So that's also the dijet constant automatically comes. Whenever you do EFT treatment, that's the main point. Whenever you do EFT treatment, it's very easy to tell, but if you look into the UV completion and look for the bound, you will see that there are other signatures also highly constant, this type of NSI parameter. So that's why it's very important to do complementary things. So whenever you take some phenomenological number like, okay, this NSI is solving T2K Nova discrepancy, but how did you get that? You need to come from some theory. And if you really look into that, you will get in one or the other issue in collider or some charge lepton flavor violation, and you need to follow and keep track of all of these.
It's constraining different operator, right? It's not the same. The constraint is not the same epsilon, right? It's 4 clocks. Okay.
So this is the dijet bound. How you can do that? Suppose
Dijet channel does not involve the receiving line.
Yeah, digest doesn't involve NSI, but you require, so I'll just write down two couplings, okay? GQ, G prime QQ, and G neo, G prime nu neo. Okay, then you can write down the epsilon of the like nu alpha, nu beta in terms of these two couplings, okay? Which will be GQ, G neo over suppose same G prime square. Okay. Now to get NSI, of course, you need to abide by the constant, right? You need to optimize it. Whenever you will do optimization, suppose the GQ you are taking it maximum. So then there is no point of talking about NSI. It will be automatically like ruled out by digest searches. So you will maximize G new coupling, which is unrestricted. Take it, suppose order 1, and vary the GQ such a way that in such model, if you get NSI, what will be the bound from the digest? You see?
So that's
So that's why you can come to some conclusion. Although it's not directly appearing, but you can do that. So as I said, like it's not so trivial, like always something appearing, some anomaly or something, we say that, okay, epsilon this value 10% is solving these problems. But it is not so easy. Whenever you are doing that, you will face some difficulty. Even if like this, I did not tell about it. There is one interesting thing also you point out. When people do this EMT approach, sometimes how it is misleading. So whenever you are taking these two couplings for NSI, you need this coupling, you need this coupling. Okay. Let me share my board maybe. You need these two coupling. That means G prime at least going to QQ and G prime can decay to also neutrino. So some simple narrow width approximation if you take, like the total decay width of G prime should be greater than G prime going to QQ plus decay width of neutrino. If you do that, you will find that this, this theoretical inconsistent region will appear. You understand, right? As long as like you are introducing these two coupling, G prime has two decay width, like two decay mode. Either it can go to quark or neutrino. I can say that like this inequality always you can write down that total decay width of G prime is greater than the sum of the G primes to QQ bar and neutrino. That you can write down. Then simply just write down in terms of the NSI parameter. You will see that this inequality is this form. So
I'm not sure if I follow because how can you compute the total with prime without the Z prime to QQ and Z prime to nu?
So G prime to QQ and G prime to nu, when you are writing down Lagrangian, you can write it down, right?
Yes.
So, but in some with approximation, like you can do the total decay weight, right? So yeah, so that if you put down, that should be greater than each individual decay, right? So that leads to this inequality.
Okay, so you are computing the left hand side of the inequality.
Yes.
I use the narrow width approximation,
Yeah.
which would start independent of which was your considered.
Exactly.
So you can end up with scenarios where the total width is smaller than the partial.
Yeah, exactly. Yeah. So that leads to this simple thing that leads, and that's why we are mentioning these. Okay, here in this plot I have not done, but it leads to this type of forms. So unique. So this just will give some complementary. Yeah.
Have you spotted examples in the literature?
Sorry.
Have you spotted some examples in the literature that people did not take care of the
Nobody take care. So
nobody?
yeah.
What do you mean by nobody? Nobody.
Like mean in collider.
Okay.
Like you see, most of like nobody means I mean the most of the people are not bothered about how it is coming with, like what is the complementary signals and what it leads to. They do not think. They just put epsilon as a number. Like it's nothing wrong there. It's also you need to have all those informations. But they are just treating as epsilon NSI as just a number and then doing whatever phenomenology they can do. But if you really look into that, if such sort of scenario whether can be realizable and zooming into it, then you will see there are certain problems, like as I said, charge electron pair violation. These are residing in the same multiplet. Once you try to do any neutron or standard interaction from the SU2L invariance, like charge electron will also lead to some pair violations. So I'm saying there are different type of community are dealing with different type of problems. But if you want to be more complete, that's why, although if you hope, that's why I discuss about neutrino mass models and so on, not to say that, okay, how many way we can do. But if something is realized, how you will justify that? What type of theory leads to this type of interaction? So that is more important. You need to write down the complete theory, low end. So, and since we know that neutrino masses and mixing are there, this is the robust evidence which we have. That means there should be some neutrino mass theory also you need to write down, whether it's a vacuum mass or medium dependent mass, you need to have some, right, which can justify this. It's not like theoretical aesthetical problem. It is there.
So in a sense, all these papers with effective field theory said like neutrino, non-standard interaction, so they are kind of suspicious. But
It's
it's
not
not one.
As I said, I think in last lecture, that EFT prescription is good, but it's not always valid. Like suppose for muon decay, as I showed you, the scale we can compute like it should be less than 250 GeV. It was very good. Like we had some estimation, then we can say that okay, some W and G boson we are supposed to discover below 250 GeV. Then from the W and G boson was discovered by UA1 and UT collaboration around 100 GeV, 80 GeV, 90 GeV. So that's kind of give you some path, but that cannot say the complete picture, as I said. Even if for the neutrino mass model construction, the EFT treatment you are doing, but whenever you are going to say low scale models, this type of expression doesn't valid anymore. Whenever you are writing down theory, it comes with many problems. So you need to work out in detail. Yeah, that's the thing. But there is nothing wrong in it. You need to look into EFT prescription and as well as like the other thing.
One more thing before I go, this part is not because the theory, the coupling has to be too big. I mean, when it,
Yeah, so that's another thing. That's
right, it's not part of it.
no, that's not part of this inconsistent theory comes from this inequality criteria. But on top of that, you are right. There is a perturbativity limit. I show in a model. No, I think I did not put that plot. But on top of that, this inequality. So whenever you are trying to get some sizable NSI for a heavy mediator mass, as you can see, you are right, that this coupling needs to be very large.
But you mean the line will be further away?
Yeah,
The
yeah,
line.
farther away, yeah. And that will lead to some perturbativity limit. So you see, it's very easy to talk about this NSI strength and so on, but it's hard to realize. Yeah, that's the same thing you can do for me in muon collider also. Suppose say people like as I said, quark NSI from here you can do for the quark NSI. When I have two fermions as quark, then you can do same thing for E plus E minus collider. Missing in lepton collider, it's better to look for monophoton signal. So in E plus E minus collider, if you look for, you can say something about neutrinos and electrons interaction. So basically you start with E minus, E plus. I don't care what is there. So just monophoton. So basically in E minus, E plus, you can look for missing ET plus monophoton signal. And that will lead to an idea in new theory, whatever the interaction strength you can accommodate if you have E plus E minus new type of interaction. Any neutrino mass model, if you write down, always you develop such sort of interactions. Strength can be different, but so you can get some room. So same thing you can do for also second generation leptons. So mu plus mu minus collider, do the same exercise. And you can, in mu plus mu minus collider, and from there you can write down all the operators. And basically here, if you see mu mu and neutrino, from the monophoton, it can be either from G prime or pi or delta plus. You can tell about this neutrino non-standard interaction with muon, second generation electrons. So that's the way you can put such or do some complementary such study. So that's it. So in collider, that's it. Like you can look for all these particles, defined signals, so lepton number, violating signals, and so on. Then also you can look for long-livedness of these particles in the collider. And then the second thing which I said, also you can look for neutrino non-standard interaction in the collider in a clever way. So now let's see in the other places like oscillation or scattering experiment, other places how you can look for. So same sort of NSI, just since I'm talking about neutrino's new interaction, this can affect also in the oscillations, which I'm doing with Iago. Like I showed this Hamiltonian, like if and in standard model, like you have this 1-1 entry due to this matter potential, but all these are zeros entry. But if you have NSI, all these entries are populated. And if these entries are populated, you can look for like whether it can lead to some new resonances and not. So then what will happen? The I think I showed you this level crossing diagram for solar cases. But here, like we are showing that even if you have suppose a large epsilon tau tau and so on, that could lead to some new resonances, which will change some expectation in oscillation experiment of the fluxes. So just I'm trying to give an overview, like what can lead to this type of NSI effects. And I already showed this diagram that Dion's and hypercamiocan defined experiments are looking at it. So this is just the timeline I have showed, like it was passed. And defined oscillation experiment, this is Dion, hypercamiocan, and other experiments are on the way. So what you can look for, this type of interaction where you can probe and so on. And then also in scattering experiment, short baseline experiment, suppose say mini boon, micro boon, LSND, Carmen, which are already happened, like these are different type of target material. And some of the experiments looking for mu mu or mu mu bar disappearance. Some experiments are looking for, like all the experiments are looking for defined signals. So short baseline means where you are not getting enough length to this oscillatory pattern. And you look for some new physics there in short baselines. And then also scattering experiment, suppose say from any dark matter direct detection experiment also. It's kind of a scattering experiment, right? Because although you are targeting for dark matter, but basically from sun, neutrinos are coming. They treat it as a background. But if you have some new physics involving neutrino also, that also you can look for. Other than that, there are several experiments like in different places. I think Coni in Brazil also, Coherent, CONAS, MINA. There are different experiments are also looking for same sort of things. Like basically you have say neutrinos are coming in and you look for electron recoil or nuclear recoil, say up or down. So that type of from the electron recoil or nuclear recoil, you can interpret about the interaction strength of the NSI and so on. So these are the things which is ongoing, and there are several possibilities. Like you can look for neutrinomagnetic moment. I have not enough time to go in detail, but if you have questions, I can talk about it. There are different possibilities. You can look for new gauge bosons or dark trident signature. All these neutrino experiments, you can look for decoherence, non-unitarity, and so on. Just the final thing which I want to say that okay, we talk about energy frontier, intensity frontier, different places what you can look for, but which is very promising and those who are interested in working on neutrino, like another thing which is cosmogenic neutrino flux, which is giving a huge defined kind of energy frontier, EV neutrinos. Like the human built experiment cannot produce such a high energy neutrinos, like several hundred millions times energetic neutrino you can produce, which is coming from the very far. So let's take a look at this ice cube experiment, which is in Antarctica. Imagine that basically all the information you get, either you get through photon or through neutrino, right? So if you go in the starry night, basically what I'm saying that you just look for stars and you can say that there is some stars because lights are coming. Similarly, imagine there are lots of neutrinos are coming in, just you cannot see. If you have eyes to see that, so that's what it is happening in ice cube. Like if you have say cosmic dynamo, we don't know this about the source, but it can be supermassive black holes or cosmic dynamo or anything where these cosmic rays are mostly protons interacting violently and producing a lot of neutrinos which are coming in. If you have detector to capture it, it can give some new information about not only about source, but also about some neutrinos, new properties, and so on. Let's look at some of the examples, or suppose say neutrino mass models and so on, how it can lead to some characteristic signal. First, one thing is that, of course, if you start with some high energy neutrinos, as I mentioned, if it is traveling enough length, then you can it's basically people consider it's almost like a vacuum oscillation. So if you know the flavor ratio, I'll just give you example, what do I mean by flavor ratio? You will have a standard expectation in 3 neutrino oscillation paradigms. What will be the expectation in these flavor ratio triangles? But if you have some new physics effect or something, while it is traveling to Earth, this expectation will be quite different. And ice cube is it's I'm not explaining it, but just want to here highlight that you have two type of signal: track signal, where you have almost 5,000 photomultiplier tube, and if you have track type of signature, that is called nu mu, and nu e and nu tau, it gives some sort of defined signal. You can discriminate between these two type of signals. One example here I want to just highlight. Suppose all these ultra high energy neutrinos are coming in, and then if it is talking to matter, you produce W, which is known as glasso resonance. So if you see the spectrum here in the ice cube, this is the spectrum which you expect the glasso resonance is this one. If you back calculate, you will see that that is exactly 6.3 PeV. Okay, that's the called glasso resonance. And now we look for this. So if you can compute this energy of the neutrino mw square over 2me, which is 6.3 PeV glasso resonance, which ice cube is looking for. There are already data. Ice cube Gen 2, they can tell more about it. The same thing can happen, suppose in radiative model, as I said, you have lepton neutrino interaction with charge scalar. Collider may be blind for this, but if you look for, suppose in this type of high energy neutrinos, suppose for 100 GeV, you can back calculate and you will see that I will expect some spectrum which will look like this, in addition to the glasso resonance. So such radiative models where you do not have right-handed neutrino, you can produce such resonances in neutrino mass models. I'm just giving you one example. You can, I think we wrote series of paper on that. In defined neutrino telescope, if you have leptoquark also, you can look for such resonances and so on. Instead of neutrino and electron, you can do with quark, and it will lead to some resonant feature in the spectrum and in ice cube Gen 2. So also another thing which another thing which I want to point out, the questions we are trying to address, suppose if you have right-handed neutrino, how heavy you can probe? So the answer is not in collider, maybe in the EV cosmogenic neutrino flux, because there your center of mass energy is quite high than the collider experiments. Okay, so and if you have right-handed neutrino, generally you can write down some dipole portal interaction where active neutrino goes to right-handed neutrino and a photon. I think in some of the places already I presented this seminar, but in Sao Paulo also I'll talk about it on Friday. So in those type of cases, you have a standard flux expectation, and when you have this type of interaction, so very heavy neutrino, we found that Grand and Poima experiment like almost like 100 TeV right-handed neutrino, even if you can probe for that. So which is much higher than the say collider center of mass energy. And these are the ongoing TeV to PeV neutrino telescopes today, KM3net, Boyka, and so on, and IceCube. And here I'm just showing defined energy range, defined experiments are ongoing. You see this neutrino energy in this scale, several neutrino telescopes are upcoming and defined. Some of them are balloon type of experiment like Anita, or some of them has like, yeah, so defined such strategy they are taking to detect the ultra high energy neutrino. So it's a kind of dawn of like neutrino astronomy and so on. You can do many work. And these are like basically I'm showing here that you can get like 4 type of information from these ultra high energy neutrinos. First of all, you can get flavor composition. You have standard expectation from there. You can say something about mu tau. You can tell about arrival times. Neutrino and gamma from transient arrive simultaneously. But if you have this discrepancy, then you can talk about some Lorentz violations and so on. And then energy spectrum. Suppose you have powerless spectrum, you can have something defined expectation also. And arrival direction from the directionality also you can tell from the neutrinos. And now I will quickly show you. I don't know whether you are familiar with these type of plots. These are called flavor ratio triangle. Generally, you read like this: fraction of nu tau you do, fraction of nu e, fraction of mu mu, and you read like this. Suppose 0.2. It's read like that means fraction of mu e is 0.2. Then you will go to this x-axis. This is 0.6, and this is 0.2. That's how you read the coordinates. It's good to know because that is very important for this flavor ratio triangle. So suppose say if you have this P gamma sources and so on, so on full point decay chain, you have mu e, mu tau, ratio 1:2:0, or muon damped 0:2 mu is 1, and tau is 0, and neutrino decay is suppose mu e, mu tau 1:0:0. So you start from here, because here mu e is 1, and mu tau is 0. And then if you have vacuum oscillation, if you take some certain distance, some 10 kpc or something, you will get to this point. And like if you have muon damped, same thing you can do, you will arrive at that point. And for the sorry,
What's this new method? Like then what's the embedding?
like from ion decay, you produce muon, and then muon again decays, right? From there.
Yes, but then is mu then.
Yeah.
Just then it's like mu medium.
Mu loses energy.
Yeah.
Okay, that's it.
Yeah, that's the called muon damp.
The neutrinos that he decays to cannot be detected by us.
Okay.
Yeah.
So the damping is the root energy loss. Yes.
So then, just wants to highlight also another work I have done with Iago. Like generally in literature, it considered to be vacuum oscillation. Then you see in the flavor ratio triangle, you will have a standard expectation where you should expect for the different sources. Now we are considering say Compton thick AGN, where like matter density is too high. So then whenever you produce this neutrino, it can go through some resonances. which we are showing, like it can go through some HL resonances or only H resonance, or like it can only go through one resonance depending on the profile and so on. So, but what we are saying that in those type of scenario, if you have matter density too high, resonance happens this around this broad line region and here. So then you will expect these flavor ratio triangles expectation will be quite different. That's what we are trying to say. So that even if you have some different sources which is very far from us, but looking at just the neutrinos, the flavor ratio triangle, you can say something about whether there is some matter effects happens beforehand or not. So in this Compton thick AGNs also how it is defined in astrophysics community, where like basically due to too much matter density where X-ray is getting absorbed and so on, you are not getting information about that. So in those cases, this is could be one way of looking at it for the neutrino telescope. And like as I said, like from the different type of ray, infrared or gamma ray or X-ray, you talk about the sources. You look at the sources in astrophysics. Basically, you tell about sources informations, but also looking at neutrino, you can get some complementary information. That's how we do discuss different things. So that's why it is quite important nowadays what basically particle physics people are doing, probing neutrino property, interaction, fundamental symmetries at the highest energies. And astrophysics people, they are basically discovering and characterizing the most energetic astrophysical sources. Now it's becoming more and more important to talk to this community, and they are exchanging ideas like experimental side. There are experimental sites, measurement sites, also there are problems which people are trying to figure out. And also like it's very important to exchange ideas between particle and astro community, which can lead to some different complementary information about neutrinos. And here I'm also summarizing that basically all the high energy neutrinos are coming in, you have matter, you forget about what new physics involved here. You can write down all type of new particle, whatever you can write down, and what sort of information get from these cosmogenic neutrino fluxes. Say for example, Lorentz invariance, quantum gravity, test of equivalence principle, fifth force, unitarity, microscopic black hole, or transition magnetic moment. All these effects you can look for. These are very trending topics. You can look for this scenario. And as you see, these many TeV to EV neutrino telescopes on the run, like 2020 to 2040. So IceCube, KM3 vehicle, like in different locations, some of them are already running in, and there are satellite type of experiments, balloon experiment, mountains, valley. These are different kind of search strategy. So it's a high time to work on different kind of neutrino properties, or what sort of information you can get from neutrinos, these cosmogenic neutrinos. I think here I will just, what is the time? Yeah, 4:30. I will not go beyond this. And I think I already presented neutrino magnetic moment in some of the places. So also in Friday, I'm talking about it in Sao Paulo. So it will more or less cover all the out. So there I'll talk about, so far I talk about neutrino interaction with matter through the any new particle other than W and G in the like say it can be scalar, electroquark, or G prime, or whatever it is. But now I'll talk about how it can talk via photon also, and why it is so important, which is neutrino magnetic moment. I will not get here time to discuss that. So that way I will.
The last
This one, right?
Yeah, I think this is update. Yeah, that was fun.
Okay. Very good.
So, just I want to highlight that there are many problems like which leads to go beyond the standard model. If you categorize like just this is just rough sketch to give you an idea. Like there are experimental evidences, theoretical motivations. You can jump into any problem, but like these are experimental evidence which strongly leads to like you need physics beyond standard model. And then dark matter, dark energy, matter, antimatter asymmetry, there are several anomalies coming and going away. So these are kind of also experimental facts. But there are theoretical motivation, also naturalness problems or strong CP problem. But here I just talk about if you have such neutrino oscillations already discovered, so you need to come up with theory which leads to these neutrino masses and mixing. And it's a multi-frontier problems. It can solve different phenomena, different things. So these are the major problems which are ongoing to like community are putting efforts to address these issues. So those who are working on neutrino and those who are not working on neutrino also, still it's a high time to think about these problems and how to deal it. And as I said, you need to be optimistic. This is PDF, that's why it is not running. But otherwise it could have run. Like you need to be optimistic. You write down your theory. If you think that is the correct one, believe in it and look for indefined signals in energy frontier or lifetime frontier, intensity frontier or cosmic frontiers, which may lead to some answer. And thank you.
Question. Which is very, very well.
I'll talk about it on Friday.
Oh, we will try to, are you going to have a Zoom week? Probably. Some of the, we'll try to mix some way. I don't know if it's going to right, but it should, we should have a this. Let's do that in the email. With the current setup fellowships, which is done with at all. But we will try to set your email for everybody.
Just to see the big revelation, favorite one.
You saw, I think.
This horizontal symmetry.
It's already removed by. What's your least favorite one?
Yeah, I cannot.
Let's turn off the camera.
There is English favorite, but like, yeah, of course, you have some personal preferences, but I'm quite open. If it is at least, it is minimal in your standard, like try to think whether that's the minimal degree of freedom you are introduced on top of standard model that is leading to these experimental facts. Then I am already motivated. If it is like if you are randomly just introducing particle without knowing why I am doing that and which I never can discriminate, then I'm not.
No, as you mentioned about lateral estimates.
Yeah.
I think has only some indication, right? It's not
Yeah.
5 sigma yet, right?
No, but that's the error one is too high, so we cannot claim that. So Gen, I skip Gen 2, which will be 10 times of the volume. So new data maybe much.
How realistic it is to think about lateral resonance sort of WR in sharing experiment, which
Okay, so that's the thing actually we were discussing if you have, but if you see the WR, that's a good question. But if you back calculate, like for W is 6.3 dB, right? For WR, it will be any high energy. Yeah, almost like a cosmic.
Need the EV neutrinos. Do you think it's beyond that?
I think it's beyond that. Suppose if I TV trip, no, that it will be beyond that.
I see. I thought it was EV neutrinos.
Unless you can have WR which is super hyperbola or something, which is
Yeah.
not possible.
Yeah.
Okay.
But there will be some other way to look around it, right? As we are discussing also, maybe some in yeah, matter effect from suppose say some other sources. It can lead to some effect where maybe WR also plays important role, not only W.
So having this high energy neutrino can only come from we have still different sources.
Sorry, higher energy.
This PV scale neutrino can only come from a heavier state or
No, these are just standard model.
say you got 6.3 PV neutrino that is kind of down.
No, this is the energy of the neutrino. This is not any state. This is the energy of the neutrino which is produced.
No, like you're producing glass oil. So yeah, you will have like different energy, which will like 10 PV or something. Do you expect the heavier state always or it can be different source of heat?
Sorry, if you get some resonance pattern, like what I showed in this track distribution, that can come from only some resonance.
Okay.
Yeah, so either neutrino matter, if you have some new resonant particle, that can lead to, in this Pauling car, you will see some resonance feature. So that can come from only the, so suppose the other than 6.3 PeV in other beams, there are some this type of elements that are appearing, that means some new particle which is coming.
But we don't know exactly how these PV neutrinos are produced. Like the sources are still under debate.
Yeah, of course, like I do not have any information about sources.
Yes.
But if all the beams are following your expectations, like that's what I'm telling. From the telescopes or the astrophysics community, they are looking for these sources. They know how far these sources are. Suppose if you are getting information from X-ray or gamma ray and so on, I'm getting some complementary information from them. Now in IceCube type of experiment, instead of looking now X-ray or gamma ray, I'm looking for neutrinos. And now I could have some expectation that what we need like along this direction, because IceCube have also good like they can tell about the direction depending on the energy deposition. Because whenever we are looking for this neon graph, which direction it is depositing energy, you can say about whether it's along the horizon or different angles. You can talk about this. So yeah, I don't know what I will answer.
I was just saying that like we have measured the PV neutrinos,
Yeah.
but it's not clear the mechanism that accelerated the particles that give rise to the neutrino peaking as PV.
Yeah, yes.
So what you're saying, for example, the flux can have a sudden shift, that's why you're detecting a resonance.
No, I was just saying that as far as I know, we don't know exactly how they are produced. Like how can you produce a PV beam given the particles you can, the same amount of particles you can use to produce.
You mentioned some sources like that. Yeah, how can they produce?
Like these cosmic ray protons, these are very violently interacting, right? This PPP gamma interaction, and this process produces fire.
In the source or in the atmosphere?
Like in the like source, yeah.
How black hole can be?
You have the accretion disk and so on, there also you can produce. There are like where it can be produced exactly we don't know. Like people have different kind of proposal and so on, so.
Like to accelerate protons that will collide with other protons or photons into pions, pion to produce.
Yes, then we use as doing like this proton charge violent can produce.
source of these neutrinos is the source of cosmic rays, and people still don't know exactly what they are.
And also which region you are exactly producing. So this is also another things which I have not talked about, like this AGN also. We don't know exactly why these neutrinos are produced.
So I think before ICTP, everybody was thinking it was obvious that they were producing jets. But now there is this, so because when neutrinos are produced, the gammas are also produced. So you should see neutrinos and gammas in the same energy range, but then you don't see gammas. So you need some opaque environment, which neutrinos go through, gammas don't. So then one hypothesis that neutrinos are produced very close to the black hole in this dense region that he was talking about. And if they are, but then, but now this is, you see now this is a total multi-messenger astronomy, because you had gamma, you had neutrinos. So things are changing, and if you have a produce close to the black hole, you have much less space to accelerate. People still don't know how that is possible. So like many problems are open.
Yeah, so that's why I said like more and more data you will tell more things about this.
It's also nice to highlight that even for like ordinary cosmic rays still have some excesses or knowledge to people who really know objects. Just look at the problem flux, for example, you can model it very well for law. But then there's some transition region for AMS2 and other experience that say that you can each have another source there. So people really don't know how water is originated. It's kind of extra just the flux.
Okay, and feel free to write to me email or something if you have some questions, you can informally chat or discuss. And I'll be here in Brazil like 2 more weeks.
Considering the manager.
Will you send to us the slides?
Sorry?
Will you send the slides to us?
Yeah, I think saying circulate the email list, so I have now the email list I can circulate. I'll just reorganize a bit and then
Okay.
and also it's all available in YouTube, so.
Yeah, because I think.
Yeah, you can send to me, then I'll try to pass to you.
So, yes.
Some policy, yeah.
Well, okay.
Thank you very much.
Thanks to thanks everyone for the thanks Diego for the timing and everything. We're very happy that you.
Thank you.